So today we're actually going to be going over two different things. We're going to start out with distributing solar energy, which ties into what we were talking about yesterday. Okay, it's going to be about wind patterns on Earth, which of course relates to moving energy around, like we talked about yesterday, moving the latent heat around. Okay, it's about convection because that's essentially what wind is. Okay, it can be related to albedo because of some parts of the Earth heat up more quickly than others. That can cause the movement of air because of the second law of thermodynamics. So it all kind of ties together, but we're going to talk specifically about the wind patterns that we see on Earth and why. Okay, and then after that, we're going to go into specific heat capacity, right, which is part of why living near an ocean is a factor that affects climate. Okay, we're going to talk kind of why the water can hold more heat than land can without changing its temperature, okay, things like that, and introducing the very simple math that goes along with specific heat capacity. Right, that's what we'll be doing today. Tomorrow, we're going to go over latent heat, okay, and then Thursday, we'll probably look at like maybe even biomes and things like that, and we should be able to get everything done with lots of time to review for the test, okay, for our unit exam. Okay. Okay, so for today, we need to understand how energy is distributed on Earth. What part of the Earth gets the most energy? The equator. The equator. Okay, it's the one that is most directly under the sun, receives the highest intensity sun.
Am I doing my physics test?
Yes. Okay. So the equator gets the most energy, the poles get the least. Okay? When we have a difference in anything, we know that there's got to be a balance, at least tried to be achieved. Right? And that's going to result in the second law of thermodynamics kicking in. Energy is always going to go from hot to cold. It's going to go from the equator toward the poles. The best way for the energy to go from the equator to the poles is through the atmosphere. We talked about that yesterday. The atmosphere is the part of the Earth that is most responsible for moving energy around. Okay? And it does that because it's the most fluid part. That's going to be wind. Convection is going to happen. Hot air is going to rise. Cool air is going to descend. And things are going to get moving. And we're going to have wind. Okay? We're going to feel that, and it's going to move not just the sensible heat, but also it's going to take moist air masses that we talked about yesterday that are carrying that latent heat from one place to another. Now, there are patterns of wind on Earth. Patterns of prevailing wind, right? Here, what direction does our wind prevailingly come from? Wow, you guys have to be more in tune to the weather. Okay? That direction, right there, southwest. Okay, that is the direction that our winds typically come from. Right? Part of that is the mountain barriers, okay, creating Chinooks and things like that. But part of it is our position on the Earth and how the convection currents that get formed on the Earth interact. Okay? We're kind of near the edge of one set of kind of prevailing winds and just off the next set. So that's why in Alberta, if you don't like the weather, wait 5 minutes, because we're in that transitional area between one set of prevailing winds and the other set of prevailing winds. And so we can, it's not a defined line, it's not a border that doesn't move, it's something that can obviously move back and forth, and we can be affected by both. How many people have heard the term polar vortex? Okay, good. So you are somewhat familiar with that. That's always big in the winter, right? Again, the polar vortex is going to get snowy and wickedly cold. It's going to be minus 40, okay, things like that. The polar vortex is a prevailing wind pattern. The polar vortex is actually always there. Okay? It's just every once in a while it gets really strong and it decides it's not happy living up near the North Pole, and it decides it's going to make everything unpleasant for us further south. Okay? And it just falls further south and affects us down here and even sometimes way down into the United States. Okay? All right, is that making some sense? So we're going to look at the role that winds play in distributing energy. Kind of talked about that. That's the latent heat, okay, and the movement of sensible heat as well. We're going to talk about this thing, the Coriolis effect. Okay? I'll show you a demo of that. And we need to recognize that global wind patterns are a product of convection and the Earth's rotation. If it was just convection, everything would move north and south. Okay? All the winds that we ever experience would just be north and south, and that would be it. But they're not. Okay? Sometimes they come from the east, sometimes they come from the west. Okay? That's the result of the Earth spinning. Now, does the same bit of atmosphere stay over top of us as the Earth spins? Okay, like, so if we're spinning around on the Earth, does the same piece of atmosphere stay with us as we go? It doesn't. Okay, that would require gases to be physically anchored to the Earth. Okay, now while there's a bit of follow there, remember that the atmosphere is fluid and it might be doing something else entirely because of convection while the Earth spins under it. Okay, and that's what's going to produce this Coriolis effect that we're going to talk about later. Okay, so the Earth's atmosphere is in perpetual motion. Okay, it's always moving. There's never a time where the Earth's atmosphere is not doing something. Okay, and that movement is striving to eradicate the differences in pressure, okay, and in temperature, right, between the equator and the poles. So if we're looking at that diagram right there, okay, this is the direction of the Earth's rotation. Okay, the Earth rotates this way, which is why the sun rises in the east and sets in the west. Okay, if we're over here, okay, on the dark side, it's nighttime, and then as we come over into the light, okay, it would appear from our perspective, okay, that the sun is going to rise in the east, okay, to our left. And then as we spin underneath the sun goes like this as we spin the other way. Okay, so the sun stays still and we spin underneath it, and then as we get to here, okay, it looks like the sun sets, even though it's really just us spinning out of its view. Okay, everybody okay with that? Now, as we do that, we move under the atmosphere, and that creates a pattern of prevailing wind, okay, near the equator that goes this way. Okay? These are called the trade winds. They were used a lot during, kind of colonial times when, the Europeans were bringing lots of stuff over to the Americas. They would use the trade winds to come over, and then they would sail up the coast of the Americas and then catch the westerlies to go home. And there was this big trade route, and that basically made kind of a circle that they would follow. Okay, so as we said, nature doesn't like imbalance or inequity. That's the second law of thermodynamics. Variations in temperature create variations in pressure, and so air moves from one area to another in order to eradicate that. That's what can cause a tornado. Okay, we talked about that the other day as well. If you've got all that warm, moist air going upwards, you create a massive low pressure area beneath it, right? And then all of a sudden, that pressure gets equalized, okay? And the cloud just drops right out as a funnel, rotates like crazy until, okay, the pressure is equalized. Okay, now, one of the major wind mechanisms, and this is one you're going to want to know because it'll be part of an answer on your unit exam. Okay, and that wind mechanism is the jet stream. How many people have heard that term before? All right, so the jet stream, okay, is a very high altitude, like up in the stratosphere, wind mechanism. Okay, its position changes all the time based on patterns of high pressure, low pressure, okay, things like that. And so its effects, or its movement, is kind of what causes changes in weather for us. If there wasn't a jet stream, we'd have the same weather all the time. Okay? But the fact that the jet stream moves around results in it being able to move large masses of air from one place to another, which is going to cause changes in weather for us. Okay? So the jet stream, like I said, it's a major wind mechanism, okay, and it's created by differences in temperature in polar and tropical regions, okay, and it is about up in the stratosphere. Okay? Now, normally, under ideal conditions, the jet stream does this, and it just goes from west to east across basically the southern part of Canada. Right? That's if everything was absolutely hunky-dory and perfect, okay, that's about where you would find it. Right? The reason it's called the jet stream is it's there a lot, and jets can access it. If they get up high enough and into the jet stream, they don't use as much fuel because they get this wicked tailwind that pushes them along. Okay? As long as they're flying from west to east. Okay? If you're flying from east to west as a pilot, you avoid the jet stream like the plague. Okay? Because you don't want to get into that. It would be like pedaling your bike into a strong headwind. You wouldn't want to do it. You'd use a lot of fuel and you'd arrive probably late. Okay? Now, catching it, not catching it isn't a big deal. If you're in it and it's pushing you along, you go a little faster, you use a little less fuel. You try and avoid it because you don't want to go into a headwind. The real problem is when you cross it. Okay? Anybody ever been in a plane and encounter a ton of turbulence, like to the point where you start to actually be a little fearful? Like back in there. It's like, all right, this is how it ends. Okay? The plane is literally shaking itself to pieces, and I'm afraid. Okay? That usually happens if you cross it. Again, pilots have an idea where it is. Our weather satellites can always locate it. We know where it is. Okay? But sometimes it grows or descends kind of rapidly, and a pilot will catch the edge of it. And when you're going across it, it's all of a sudden like you've got just a side wind, okay, kind of out of nowhere. And the pressure changes rapidly. And if your air pressure changes, your wings don't produce as much lift. And the plane drops really fast. Anyone been in a plane when it just all of a sudden just kind of dropped? It's why you have to wear your seatbelt all the time. Okay? Even then they come on the thing. The captain has turned off the fasten seatbelt sign, but you should stay in your seat and keep it on. Because if the plane suddenly hits one of those pockets, okay, or crosses the jet stream and drops suddenly, if you're in your chair, okay, the plane drops, what do? Well, actually, you don't go up. The plane drops and you sit still. Okay? It's the same thing that causes you, if you're not wearing a seatbelt, to go through the windshield in a crash. It's called inertia. Remember we talked about that in the physics unit? Okay? So if I'm in a car going 100 kilometers an hour and I crash, the car stops. But if I'm not fastened to the car by my seatbelt, which would be dumb, but okay, if I wasn't, I would keep moving at 100 kilometers an hour. That's bad. That's why you have to wear your seatbelt. And it's why you have to wear your seatbelt in an airplane. If the airplane's flying nice and level and all of a sudden drops, you sit still. And if you're not wearing your seatbelt, it looks like you fly up into the air and smash your head into the overhead bin. Okay? And it's actually happened on occasion where flight attendants and sometimes passengers have their necks broken. Okay? If they hit a really big pocket of cold air, it looks like they just suddenly fly up in the air, but actually what's happening is the plane is dropping rapidly. Okay? And if you're not seatbelted in, okay, you hit the top, you hit the roof. Okay? So with the jet stream, okay, its location can change depending on high and low pressure, and that's going to cause changes in weather. So in this particular diagram here, okay, the jet stream is this purple kind of hazy line. Now, this area of high pressure is not normally here. Okay? This is kind of an odd situation. Okay? And so it's caused the jet stream to move up. Okay? But because circulation around a high goes this way, it forces the jet stream really quickly around it. When the jet stream comes by this way, all this cold air up here gets pulled down with the jet stream. Okay? And so this area here gets cold weather. If this happened in the wintertime, this would be kind of like a polar vortex kind of idea. Okay? Now, the jet stream almost never does this, but in this case, it actually got sent back out into the ocean and then came back across its normal route. Okay? But as it comes along here, it's gone out to the ocean. What is it bringing with it? Moisture. Yeah, water. It's going to pick up moisture, moist air masses, things like that, and bring them here. Bring them back to an area that it's just caused a whole bunch of cold air to come towards. When you get warm, moist air meeting cold, dry air, you get bad stuff happening weather-wise. Okay? You see how it says on there, unsettled? What part of the United States is that going across? I'll give you an idea. The states it's going across are Ohio, Oklahoma, and Kansas.
Tornado Alley.
That's Tornado Alley. Okay? Then the jet stream normally goes kind of across here. Okay? Which is why that area is normally quite unsettled. Okay? And same for us. If the jet stream does this little pattern, which it does a lot, it also does the same thing across here. Okay? We're the Tornado Alley of Canada, so we get that same effect. Okay? So it can move all these moist air masses, heavy air masses, whatever. It can move them around based on its position. So what does the jet stream do? It helps move energy, specifically latent heat. So the jet stream is something that meteorologists watch, okay? Because the position and movement of the jet stream is really what allows them to predict changes in the weather. All right, now I say predict because sometimes the jet stream looks like it's doing one thing and then it turns around and does something completely different and completely unpredictable. Okay, that's why I don't like using the weather app on my phone. I prefer to use my weather rock because it's always right. You guys ever seen the weather rock? It's this rock and you hang it outside your house on a string. If the rock is wet, it's raining. If the rock is moving, it's windy. If the rock is white, it's snowing. Okay? If the rock is gone, you should seek shelter. But it's always right. I tell you, it's way more accurate than the weather app on your phone. All right, so that's what the jet stream does. Make sure you know that because that's going to be part of the question on your unit exam that says, how does energy move from, the equator to more northerly parts of the world? This is one of the mechanisms, okay? Along with convection and things like that. Okay, so global wind patterns look like this. Okay, prevailing winds in an area tend to come from the same direction. Again, tend to, it's prevailing, they're not always going to do that, and are influenced by the rotation of the earth and convection currents. All right, so what happens is, near the equator, where we get the most intense direct sunshine, the air gets hottest. All right, that air moves up, okay, hot air rises. Well, when it does that, it can't just go up or it would create a vacuum underneath. Okay? Something has to move in to replace it. Okay? That something is cooler air from the north. Okay? So we've got the hot air rising right here, okay? And then we have cool air moving in to replace it. Okay? Now that air that's risen can't fall back down because it's already been replaced. All right? So what happens is the air starts to circulate. Okay? This is a Hadley cell or a convection current. Okay, they have different names for the different cells, okay, but we can call them all convection currents because they basically are. Okay, so the hot air rises, the cool air descends. Okay, this hot air is now further aloft, okay, or at a higher altitude and moving north. Okay, this air is moving south. When the hot air that's risen gets to the horse latitude, so that's about 30 degrees north, okay, it starts to come back down. But because it came from the equator, it's still generally warmer than the air that's here. So it gets kind of pushed along the surface. Okay, so that warm air moves along the surface and gives us a southerly, generally southerly flow of wind. Okay, everybody with me so far? Okay, so this is what's called a ferrule cell. Okay, it's just another example of a convection current. When that air gets to here, okay, it's still warm because it's near the Earth's surface. And it's meeting air that's coming from the north, which has got to be cold. So it rises. Okay, and it creates this convection current that's going on here. Okay, and then above that, you have what's called the polar cell, or sometimes the polar vortex. Okay, it's rotating like this around the pole. Okay, and it's going to bring cool air from the north because the air that's there is meeting this warm air from the equator. So these two are both going up, okay, at this latitude. Okay? Both of them are rising because they're warm and going up, okay? And that's going to cause cool air from the north to come down. Now, where are we located? Right about there. Okay? We're right at the very northern part of what we consider to be the westerlies. Okay, which is why we typically get southwesterly winds, right? But every once in a while, our winds come from the north, typically from the northeast if we're getting them, and that's because that polar cell or polar vortex has descended far enough that it's now affecting us. Okay? Again, these are not hard and fast lines. Okay? They're general areas where these things tend to start and stop. Okay, so we've got these convection currents going on, but the whole time that this vertical movement of air is going on, what's the Earth doing underneath? Spinning. Okay, now, Not that any of you would do this because it's not safe, but if you stick your head out the window of a moving car, okay, even if it's not windy, does it feel windy? Okay, so the air is not moving, you're moving through it. Okay, so it feels like the wind is coming in your face, but it's really you going through the air. Right? Well, the same thing happens with our wind patterns. As the air is doing this, circulating vertically, the Earth spins underneath it. So near the equator, you've got cool air that's moving downwards from the north. Ooh, that's a terrible color to pick. Okay, and I can't use that because that represents hot. Go back to purple. Okay, so this air is moving down from the north. Okay, but while it's moving down, the Earth moves this way, through it. Okay, and as it moves through it, it makes it seem like it's not coming straight down, but that it's being deflected a little bit. Okay, so in actual fact, the air here is moving to the north from the south, but we're spinning underneath it as it does it. So it makes it seem like it's coming from the southwest instead of straight south. Okay, this is the Coriolis effect. Okay, it's a perceived change in direction of the winds because the Earth is rotating under its own atmosphere, while its atmosphere is trying to do something else. Okay? Everybody all right with that? All right, so here's what you need to know. You need to know about convection currents, and you need to know how they look at each altitude, or at each latitude, sorry. Okay? And you need to know what that causes in terms of prevailing winds. So near the equator, it causes the winds to prevailingly come from the east and northeast. These are the trade winds. Okay? Because Europeans would sail down like through Spain and Portugal, okay, pick up all of their goods, and then they would catch these trade winds, which would take them across the Atlantic Ocean to the Americas. All right? When they would get to the Americas, they would drop off their goods, pick up whatever things they were going to pick up and take back to Europe, and then they would sail up the coast here using the Gulf Stream, which is an ocean current, until they got into the westerlies. And then the westerlies would take them back to Europe. Okay, and they would just keep making this cycle. So they were called the trade winds because, of course, they assisted with trade from Europe to the Americas. Okay? These ones here are just simply called the mid-latitude westerlies, and then you have the polar easterlies or polar vortex up here at the top. Okay? Now, should you know the term trade winds? I would, okay, if it were me. All right, so I'm going to kind of show you what this looks like here with this little demo. This volleyball only has one purpose. Every year I pull it out for this demo. Okay. All right, the volleyball is the Earth. Okay, the Earth spins this way. Okay, now if I'm at the equator, air is trying to move from north to south. Okay, so it's going this way, but the Earth is spinning underneath it while that happens. Okay, and so we've just said that then I don't feel like the wind is coming from the north. I feel like the wind is coming from the northeast. Okay, because as the Earth spins underneath it, the air moves from north to south. So what kind of a shape does that draw? I got to concentrate. It's like tapping your head and rubbing your stomach at the same time. Got to do two different things. Okay. You ask my wife, I do not multitask well. Okay. Oop, I lost it. Okay, so I moved the marker straight down. What did I draw? A mess. But does it curve this way? Okay? I know it's terrible. Yeah, it's okay. You're not going to hurt my feelings. We'll try again. Okay, I'm going to go straight down, but I'm going to rotate the ball this way. Okay, so going straight down, rotating the ball at the same time. That one was better. Okay, curves this way. All right, so the wind's trying to move from north to south, but the Earth rotates underneath it as it's happening, makes it seem to someone sitting on the Earth's surface that it's coming from the northeast. Okay, that's how the wind gets deflected. The same thing happens at our latitude, except because we're going upwards, okay, it actually gets deflected this way. okay? So as I try to move it upwards, okay, and I spin this, I get a curved line the other way, okay? Remember that. That's one of the worst ones we've ever done. Other ones are much straighter. Okay, so that's the Coriolis effect. Should you know what the Coriolis effect is? Okay, because maybe Mr. Coderre is going to ask you a question on the test about how prevailing wind patterns happen. And you would say, well, they're the product of convection because there's an imbalance of thermal energy, so hot air rises and cool air descends. But while that's going on, the Earth spins underneath the atmosphere, causing this deflection of air, making it seem like a wind going from north to south is actually coming from the east. Okay? You've got to be able to explain that. Okay? All right. Yeah. All right, so this is just another diagram, the same thing, the Coriolis effect. Okay, so that causes the trade winds here near the equator, okay, and the polar westerlies, okay, up here. Okay, so we get things that come from the southwest, whereas at the equator they get it from the northeast. And here at the pole, they also get northeast because it's moving from north to south. It gets deflected in the same way. Okay, and so we know if we get a wind from the northeast, that it just means that polar vortex has descended a little further and is now affecting us. Okay, now you can't see this in the Earth's atmosphere because the Earth's atmosphere is transparent. Okay, but you can actually see these bands of wind, okay, that are diagrammed on all of these diagrams, right? Here's the equator, and then there's this other band of wind, and this other band of wind, and they're going in different directions. Okay? It's hard to see that on the Earth because you don't see the movement of the air on Earth. But on a big planet like Jupiter that has a roiling colored atmosphere, you can actually see this happen. And you can see the different stripes, okay, of those wind bands going up the planet. And when you actually watch Jupiter like in a movie, okay, you can actually see the parts of its atmosphere going opposite directions past each other. It's actually part of the reason why the Great Red Spot is able to keep going for so long. The Great Red Spot sits right at an interaction of winds going this way and winds going that way. So one side of that storm gets pushed this way, the other side of that storm gets pushed that way, and that thing just rotates and rotates and rotates and keeps going because it's constantly being fed on both sides. Okay, everybody with me there? Okay. Now, I think I actually have a video of that. So this is what we were talking about, just they have better animations than I can draw, so it's better to have you watch those. Okay? All right, so Coriolis effect, that's what we were talking about, okay, as the Earth spins underneath its atmosphere, okay, and its atmosphere is trying to do one thing, the spin of the Earth causes it to be deflected while it's moving, okay, and so that's all you need to know about the Coriolis effect, okay, is that it's going to produce those deflections from east to west and west to east, okay, on the different parts of the Earth, okay, they had a better demo of it than I did. Okay, that's the Coriolis effect. If you roll a ball down from the North Pole to the equator, it's going to end up over here because the target's going to move underneath it. Okay, so quick questions here. Okay, describe the effect of unequal distribution of thermal energy. Wind would be my answer to that. Describe what the effect of it is. The effect of it is second law of thermodynamics kicks in, convection happens, that's wind, that's movement of air. Okay, that's going to help move that energy around. Okay, Coriolis effect causes the deflection of those north-south winds that are trying to happen because of convection. Okay, it moves underneath it while it's happening. That makes us have easterlies or westerlies depending on our latitude. Okay, again, another reason why latitude affects your climate. Okay, and what are the trade winds? They're the easterly winds near the equator, and the jet streams are those high altitude winds that are the result of interacting wind patterns coming from the equator and coming from the poles, okay, at those latitudes. Okay. Jet streams move what kind of heat? Latent heat. Okay, that's an important thing for you to remember when you're describing the role of the jet streams. They move that latent heat, that moisture-laden air, okay, and all the energy that it contains. All right, that is all we're going to do with that. I'll give you guys about a 3-minute break here before we talk about heat capacity. Okay? Yes. All right, so next thing we want to talk about here is heat capacity. All right, now heat capacity is very basically how quickly something heats up. Okay, it is a characteristic physical property. So if you think back to the chemistry unit, we did a lab on physical properties. The physical properties we were worried about were like color, odor, solubility, aqueous conductivity, and pH. All right, well, specific heat capacity is another characteristic physical property. Every substance has a different specific heat capacity. And what that means is one substance might get, if I expose it to 20 joules worth of heat energy, it might raise its temperature by 20 degrees. Whereas another thing, I expose it to exactly the same amount of heat energy and its temperature only goes up 2 degrees. Okay? They both absorbed the same amount of thermal energy, but one of them got a lot hotter. Okay? That's specific heat capacity. Some things heat up very easily and very quickly because they have a low specific heat capacity. Other things heat up very slowly because they have a very high specific heat capacity. Water has a very high specific heat capacity. Okay? What that means is it takes a lot of energy for water to change its temperature. Okay? So if I live in Vancouver, I get the benefit of that in terms of my climate. Okay? That's why being next to the ocean affects your climate. The ocean can absorb huge amounts of solar energy, and its temperature is only going to go up a degree or 2, okay, because it has a very high heat capacity, right? That's also going to mean then that the air that's surrounding it isn't going to get very hot, okay, because if it does, the energy will go into the water, and the water won't heat up very much, okay? And the opposite is true in the wintertime. As the air gets really, really cold, energy flows out of the water and into the air. Okay? But the water's temperature isn't going to change very much. Okay? And so as energy flows into the air will match the temperature of the water and they'll stay about the same. That's why they never get really, really cold in coastal areas where the ocean doesn't freeze. Okay? Because water has a very, very high specific heat capacity. Right? What are some things that heat up very quickly? Metal. Yeah, most metals have a very low specific heat capacity. So they heat up very, very fast. Okay? Gases tend to have higher heat capacities, in general, not always. Okay? But water would be one that has a very, very high heat capacity. Okay, so the formula that goes along with heat, that's all you need to know about specific heat capacity, by the way. That's what it is. It's the amount of energy something can absorb with a change a change in temperature. Okay, so our units for specific heat capacity are joules per gram degree Celsius. Okay? In other words, how many joules of energy can be absorbed by 1 gram before 1 degree Celsius change happens? Okay? So if something has a specific heat capacity of 5 joules per gram degree Celsius, what that means is if I have 1 gram of that substance and I put 5 joules of heat to it, it's going to change its temperature by 1 degree. Okay? If I put 10 joules of energy to it, it'll change the temperature by 2 degrees. Okay? All right. Now, here's the formula for specific heat capacity. E is energy, and that's going to be in joules. Okay? M is the mass, and we're back to using grams for this because now this is thermal chemistry. Okay? Chemistry uses grams. Okay? And then delta T, delta always means change. It's the change in temperature, and that is in degrees Celsius. All right. Now, what's C then? It's the one I left out. C is the specific heat capacity. Okay? And that is different for each material. So if I gave you a question on a test, I would have to tell you what the specific heat capacity was so that you could finish the calculation. I'd have to give you C. Okay? Unless, of course, I was asking you to calculate it and I gave you everything else. All right, so is this formula going to be pretty easy to use? everything's just multiplied together, right? M times C times delta T. So if I wanted to manipulate for M, what would I do with C and delta T? Divide it over to the other side. That's all you ever have to do, okay? If you're solving for anything other than E, divide the other two things over to the other side and leave that thing by itself. Okay? Super easy to manipulate, nothing like what we were doing in the physics unit. Okay? Really, really easy to use. All right. Okay. Let's do a few examples. Copy this one down, okay? And anytime I give you a new formula, I go through all the manipulations of the formula. So give you a minute to write this one down. Okay, this is the easiest of them. All right, so on this one, we're looking for how much heat. That's going to be that we're looking for E. E is energy. Okay, how much heat is needed to raise the temperature of 150 grams? What did they just tell me? Mass. Okay. Of water. Okay, when they tell me water, in this case they actually told me what C was. Sometimes I might have to refer to the chart in my work booklet, because in your digital workbook for this unit, there's actually a chart of common specific heat capacities that you can look at. Okay, in this case, they told me the specific heat capacity for water is 4.2 joules per gram degree Celsius. Okay, so that means that water takes 4.2 joules of energy to raise 1 milliliter of water by 1 degree Celsius. That's a high heat capacity. Okay, and we're changing its temperature from 5 to 85 degrees. What's my temperature change? 80. Yeah, okay, it's just simple math. You just have to subtract the two numbers. Okay, 80 degrees Celsius. Okay, I'm looking for E. My formula is E equals MC delta T. So M times C times delta T, and I have all three of those numbers. 150 times 4.2 times 80. All I have to do for that. Okay, so that's going to take 50,400 joules worth of energy. That's a lot. Okay. All right, questions on that one? Very straightforward. Okay. So on this one, yeah, I'll have you copy this one down, but we're looking for what material. What part of the formula will tell me what material it is? C, yeah, the specific heat capacity, because it is specific to a certain material. All right, so I'll give you a minute to get that one copied down, and then we'll walk through it, and I'll actually get that found here. Okay, let's quickly look at this one. So we already said we're looking for the material, which means we're looking for the specific heat capacity. Okay, they told me it's a 100-gram cup. So what did they give me there? Which part of the formula was he given with 100 grams mass? Okay, and it takes 4,200 joules of energy. So outright they told me energy here. Okay, 4,200 joules. Okay, and we're raising the temperature from 12 to 62. How many degrees is that?
50.
50, exactly. Thank you, Reese. Okay, so I've got M, I've got E, I've got delta T, and I'm trying to solve for C. So I would divide both sides by M times delta T. I've got my formula to solve for specific heat capacity. So we would take our 4,200 joules and we would divide it by 100 times 50. 4,200, whoop, not 1,000, 4,200 divided by 100 times 50. Okay, so it's telling me the specific heat capacity is 0.84. If you look in your digital workbook package for this unit, you will see that 0.84 joules per gram degree Celsius corresponds to glass. Okay, that kind of makes sense. It's a cup. Cups can be made out of glass, so that one makes sense. Right? If you'd have got that the cup was made out of methyl alcohol, then you probably did something wrong. Generally, cups aren't made out of liquids. Everybody okay with that idea? Is this a terribly difficult formula to use? Okay. All right. This is as tricky as they get.
What's the units?
Joules per gram degree Celsius. Sorry, I didn't write that down today. I think I wrote it on the first slide, but I didn't write the answer here. So 0.84 joules per gram degree Celsius. Okay, so this next question is as tricky as they get, only because it has one extra step at the end. All right, so we are looking for the final temperature, okay, of a 185 gram block of iron. Okay, and just so you know, according to your chart here, iron has a specific heat capacity of 0.460 joules per gram degree Celsius, because you'll need that. Okay, initially at 7 degrees Celsius, if it is heated with 200 joules of energy. All right, I'll give you a couple minutes to try that one before I go over it. All right, so here's what we know. We know the specific heat capacity. We know the initial temperature is 7 degrees Celsius. We're looking for the final temperature. Okay, and we're told the amount of energy, 200 joules, and we're told the mass, 185 grams. All right, our formula doesn't have final temperature in it. It has change in temperature in it, right? But if I found the change and I know the initial, could I find the final? I could, because generally delta anything means final minus initial. Agreed? Right? We've done this a whole bunch of times. If I know the initial and I can calculate delta using this formula, all I have to do is take delta and add the initial and I've got the final. That's the extra step on this question that the other ones wouldn't have. You'd have to add two numbers at the end, okay, on this one. So what we want to do is we want to find the change in temperature. So we're going to divide both sides by MC. Okay, and then we're going to plug in our numbers. 200 joules divided by 185 times 0.46. Alright, so 200 divided by 185 times 0.46. Whoop, not 182. 185. Alright, so it looks like it is only changing its temperature by 2.35 degrees Celsius. So if it started at 7, what's its final? 9.35 degrees Celsius. That would be 7 plus 2.35. Okay, so 9.35 would be my final temperature. Okay, like I said, that's as tricky as they get, and it's just, it has an extra addition operation at the end. Okay. All right, questions on that one? Come on. Okay. Let's have you guys try one and 1 and 6 for right now. Okay, so the two that are circled in red. Okay, 1 and 6. Let's have you guys try those. These are also on in your digital workbook if you want to look at those. The answers are there in bold. What you will need from your booklet is the list of heat capacities. Okay, and they are on the very second page here. Okay, so you've got the title page first, and then so you got the title page there, and then underneath that you've got all the heat capacities that you would need. Right, so you can find them all there. So you'll need that for number 1, but you won't need. I don't think you need it for number 6. Nope. No, you've got the heat capacity there for that one. Okay. All right. So give those 2 a try.